Students, I'm going to be presenting my screen right now. Can you try? Please tell me if you can see my screen, okay?
Yes, sir.
Okay, sir.
Can you all see the screen, students?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, sir. I have your PPT ready for you. Okay. Sir, could you unmute your mic? There.
Are you able to see it on full screen?
Yes, sir.
Sir.
Yes, sir.
Okay.
Yes, sir.
So let us move ahead. So Aaron, now can I go ahead with this, or you will have to?
You just have to tell me if you want to change the slide, sir. That's all.
Next slide.
Is the slide okay, sir? Oh. Students, if you all have the answer to this question, you can enter it into the chat box.
This was this puzzle that you were all trying, and then many said that it is not possible. Some Angad and others are saying it is possible. So without now going discussing about it, let me move ahead. Next slide, please. So let me try to do it. I will do it for you, sir. So I have inserted plus after 1, plus after 2, plus after 3, minus, plus between 4 and 5, 5, then minus 6, minus 7, plus 8, minus 9, minus 10. This gives me minus 17. So you can take any signs. It's just an example. Next. Now, see, it's minus 17. And then minus 17, I have to make come as close as possible to 0. So what I will try to do is that I will make everything 0 if possible. Sorry, I will make everything positive now. I will try to make it positive. Or I will do something else. Now see, from the 17, I have changed it to 1 plus 2 plus 3 minus 4 plus 5 minus 6 minus 7 plus 8. Now I have made minus 9 to plus 9. So now what it happens, this is minus 1, 7, this is 0, minus 1, minus 2. So I am quite close. Next slide. Wonderful. We are almost there. Try it yourself. You have tried. Now, can someone, how does the sum change in every attempt from the previous sum? Who can answer? The question is, how does the sum change in every attempt from previous sum?
Because of the operation.
Yeah, because of the operation.
Sir,
Yes.
because it changes from plus to minus, sir, because of the operation only.
Yeah, suppose I make everything I kept the same. In the expression before 3, it is minus. So I have to make minus 3 to plus 3. Now, how the sum has changed? It was minus 3. Wait a minute, Aaron. So in the sum, it was minus 3. Now in the next, it is plus 3. So by how much the sum has increased?
So by 6.
6. Now I will keep, so there is some expression in which there is a plus sign before 2. There is plus sign before 2. And my whole sum is greater than 0. So I make plus 2 to minus 2. By how much the sum will reduce?
Minus.
So 4.
4. Next slide. Next slide. So what is your observation? The observation is that whenever I change any sign, the sum changes, either increases by an even number or decreases by an even number. Is it okay for you? Is this? Because I have said that now just don't look at the calculation here, but just understand that if I make, say, any change from plus to minus, the sum is going to decrease by an even number. Suppose I make plus 5 to minus 5, it will decrease by 10. But if it was minus 7, I make it plus 7, the sum has increased by 14. Right? Is it okay?
Yes, sir.
Yeah. So now, if I put everything positive, then 1 plus 2 plus 3 plus 4 till 10 gives me 55. Isn't it?
Yes, sir.
It gives me 55. And you reduce, say, from 55. Now you have to reduce. So you reduce from 55 all the time by an even number. All the time you are either adding an even number or reducing by even number. I will repeat, this is an important statement. From 55, you can increase the sum by an even number or decrease the sum by an even number. So how will the sum instead of 55 will look like? 55 is an odd number. 55 is an odd number. Now you add an even number. What kind of number you will get? Odd or even?
Sir, odd.
Odd. If you reduce from 51 an even number, which type of number you will get?
Sir, again odd.
So you
Can
do
be
anything. You
even
do
or
anything.
subtract from odd.
With this kind of operation or the condition, if the sum is going to increase by in even number or decrease by an even number, you are always going to get an odd number. Is 0 odd? No.
No, sir.
So you can never get the sum. Next slide, please. Next slide. Yes. So I have now explained. Next slide. Now you see the beauty of this example. We could have tried in various ways to change the signs. Sometimes I got -1. Sometimes I will, if I change the signature sign of 1, I may get +1. Then I can do something else. Yeah, I can keep on doing, keep on doing. My dinner will be waiting and then it would be taken out. So I will remain hungry throughout the night. But I cannot solve it. So the problem here is that I have conclusively proved that this cannot be done. That this cannot be done, I have conclusively proved.
So how could you have done that?
See, I did it just by the property of even and odd. See, odd plus even is odd, odd minus even is odd. So the sum initially is odd. So by changing, increasing or reducing the sum by an even number, I get always an odd number. But unfortunately, 0 is not an odd number. So you can never get sum 0. And we conclusively proved that the exercise cannot be done. Generally, this is very difficult to prove. Okay? Any questions?
No, sir.
Next slide.
No, sir.
So are you happy to see this kind of proof for the first time? I think
Sir.
you have seen such a kind of a proof for first time.
Yes, sir.
So it's beautiful. Now what I am saying is everything that you know. So even integer is an integer divisible by 2. Tanishka said, sir, what are you saying? I know that from 3rd standard. It can be written as 2k, where k is an integer. Odd integer can be written as 2k plus 1. Alicia says, yes. Stop it, sir. I know it from the 3rd standard. I am now in 8th or 9th standard. But I am just saying that all even integer numbers, I will put one box. All even integers I am going to put in one box. All odd integers I am going to put in box. So now you see, infinitely many integers are there. Infinitely many integers are there. And in how many boxes we have put them? Angad, sorry.
Yes, sir.
In how many boxes I have put those infinitely many numbers?
Sir,
Even and odd. How many?
even and odd. Sir, two
How-
of them.
2. From infinity to 2.
No, sir, infinity to, sir, it can even go to negative infinity.
Yeah, means infinite integers are now sitting in 2 boxes only. Finitely many boxes. Only 2 boxes.
Sir, odd and even numbers.
Yeah. So I am putting even everything in one box, all odd in one box. So there are 2 boxes. Next slide. That I can put them in 2 boxes is not that great. But these 2 boxes are interacting with each other in a very, very definite manner. They interact with each other in quite a definite manner, that even plus even equal to even, odd plus even equal to odd plus odd is even, and even into even, even into odd, even, odd into odd is odd. See,
Yes.
what I am saying is there are 2 boxes. There are 2 boxes. Is it like what, Alicia? There are 2 boxes. You choose anything from the even box. You choose anything from the odd box. Their product will sit in the even box. Negative you have
So,
chosen.
sir, like example, 3 plus 3 gives 6, so it is even.
Yeah.
Even.
So let take any two from odd, add them, they will go to even box. Take one,
Okay, sir. Thank
one
you,
from
sir.
even box, another from odd box, add, they will go into odd, irrespective of what you are picking up. That is the beauty. That is the strength. Come anybody, you will have this rule. Next slide. Yeah, next slide, please. Again, next slide, please. That's what I said, that we define these operations. Now, this is for you. And actually, if I can get a whiteboard and I can annotate on it, that may be better. But anyway, have you understood? Ria and her friends, a few boys and few girls. A 15 is not an even number, invariably. Ria and her friends, a few boys and a few girls, stand in a circle. They stand in a circle. It turns out that both the neighbors of each child is of the same gender. Right? So if Tanishka and Angad are standing next to each other, Angad is to the left of Tanishka, then a boy is to the right of Tanishka. Have you understood? And to the right of Angad is Tanishka. To the right of Angad is Tanishka. Then to the left of Angad is a boy or a girl. Can you tell me?
Girl.
Huh?
A girl.
Yeah, a girl. Now tell me, if there are 5 boys, how many girls are there?
So, 4.
How?
Sir, because one is odd and the other is even. And so if
Somebody thinks 5. No, just look like that. See, B, G, B, G, B, G, B. However, the last B and the first B are same. You see. Now let us start with Tanishka. Then to her left is Angad. Then then Sanvi. Then Nisha. Then Alicia. Then say Gaurav. See, now what is happening? I can pair everybody to the person to left. Now I am, yeah, Tanishka. Tanishka, you want to ask something?
Sir, is it 5?
Yeah, it is 5. And why I am telling you is, every girl can pair herself with the left-hand side boy. So GB. Now again, next is GB. GB, yes, 5 boys and 5 girls. Next slide, please, Aaron. I'm troubling you. Now the next,
No problem, sir.
yeah, next puzzle. Back. That 22, back. This. This is it. The product of 22 integers is 1. So that their sum cannot be 0. The product is 1. The sum cannot be 0. Now again, we want to prove something is impossible. Okay, now. Now Adya. Adya, tell me if the product of 22 integers is 1, what can you say about those integers? Can there be 2?
Product.
Ganesh, can there be 2 in those integers? The product is 1 of integers. Aditi Achar, can there be 2? No. So how are Ankit? No. But how are they now? See, 2 is not there, but then what kind of integers? Which integers can be present in that?
So minus 1 and 1.
Minus 1 and 1. Excellent.
Yes, sir. Positive
So
one and negative one.
now tell me, now it's odd and even again. It's odd and even, not minus 2. Because product will be greater than 1. Yes, only minus 1 and 1. Now, how many ones are there and how many minus ones should be there?
Sir, if the sum is 0, then there should be...
See, no, wait a minute. Somebody said that 11 ones are there. Then 11 minus ones are there.
Sir, if the sum is 0.
But if 11 minus ones are there, the first condition given is the product is 1. So if 11 minus ones are there, 11 minus ones, their product is minus 1. Their product is minus 1. And other 11's product is 1. So the product will be minus 1.
Okay, sir.
So the number of minus ones is either, which is, will it be odd or will it be even? My question is simple. Now we have to give, Arshit Singh says that the number of minus ones is even. I don't think Aparna likes this answer. Aparna? Okay. So, is everybody convinced that the number of minus ones should be even? Because minus 1, 1, minus 1, 1. So, minus ones should be paired. See, Inavli sisters, Angad, and Sanvi, they are only talking. Let others also talk. Okay, so minus ones are even. Then 1 will be something. So, see, if minus ones are 12, minus ones are 12, 1 is 10. The number of tens is 1. Now there is only one step remains to show that their sum cannot be 0. Now independently, when will the sum of minus ones and ones is 0? Previous slide. So when will be the sum of numbers 1 and minus 1 be 0? Can the number of ones be greater than number of minus ones? No. The closest sum, no. My question is simple. How will be the number of ones and the number of minus ones? Don't they have to be equal? Don't they have to be equal to get the sum 0? Yes.
Sir.
Gaurav says yes, they should be equal. But then if they are equal, then 22 upon 2, yeah, number of minus ones is 11, number of plus ones is 11, but
Sir,
11
then
minus
neutralize
1,
and it should be 0.
yes. So the product will be minus 1 and their sum cannot be 0. Next powerful result with a simple argument of odd and even we have proved. Yeah, next slide, please. Yeah, now I have asked some funny question, which I might not dare to answer, but then 1, 2, 3, 6, 7, 2, 3, 4, 6. Is it a square? See, when I am asking you this question in 50 minutes lecture after say 20 minutes of it, there has to be some trick. I am not going to ask you to calculate square root. The trick is given below. Why Avita no? Avita Carvalho. Why no?
Sir, it's Bruno Fernandez. I joined from my mother's email. That's why I put these two as no, because yes, like 23 and 46 is not a square and 19 is also not a square.
But why is it that the last two digits should be square?
Let me check on the phone.
Now 121 is 11 square. Is 21 a square?
Well, the answer is
Arshit, why? Why it is not no? It is no. Yeah, I may be taking wrong names because you may be joined by your parents and you are not renaming yourself. But
So,
why no?
so no number can end with 6. No square can end with 6.
36. Just see below. Just see below. 2k is an even number. 2k plus 1 is an odd number. So square of a even number is 4 into k square. So it is divisible by 4. Square of an even number is divisible by 4. Agreed?
Yes.
Yes, sir.
Yes. So this number divisible by 4. Now it's even ending. The ending is even, but is it divisible by 4?
No.
It is not, because
No,
last
sir.
two digits you take, they should be divisible by 4. Right? So
Yes,
this
sir.
is not a square. We have not calculated anything. So it is not a square.
Yes, sir.
Great. You are really great childs of Goa. I thought of doing all this calculation. You told me in 2 minutes. Great. Oh, but then I think 6347619 is a square.
No,
Why?
because it's not divisible by 4.
Yeah, it is not divisible by 4, but then any odd number square will never be divisible by 4. 3 square 9, 7 square 49, 11 square 121. But what I am saying here is, when divided by 4, it gives remainder 1. Do you understand this part? Now 2k plus 1 bracket square is 4k square plus 4k plus 1. 4k square and 4k are divisible by 4. So when divided by 4, the remainder has to be 1. If it is a square, the remainder divided by 4 has to be 1. And for division by 4, you just check last 2 digits. Divide 19 by 4. What is the remainder? 3. Arun, what is the remainder when 19 is divided by 4? 19 divided by 4, remainder is
1.
19. 2.5?
1.
1. 4 4s are 16. 16 plus 3, 90. So remainder is 3, but no square number when divided by 4 gives remainder 3. So this is not. Yeah. Aaron, the Goa students are excellent. Your Infinity 3D students are excellent. Isn't it, Vedanti? Next slide. Okay, now there is a wheel and I am writing 0, 1, 2, 3. Next slide. Huh. See, we have divided the infinitely many numbers into 2 groups, even and odd. But if I divide them in a few more groups, but finitely many groups, such that again those groups interact with each other, there is an operation of plus and multiplication between them, and the properties are very nice. The operations are very well defined. So do you know division algorithm? That means if there is an integer a and non-zero positive integer b for the time being, so I can write a equal to bq plus r, where q is quotient and r is remainder. So a equal to b into q plus r is remainder. And what is the condition on the remainder? 0 less equal r less equal b. That the remainder has to be between the divider and 0. Should be less than the divisor and greater than the
0.
greater equal 0, less than the divisor. Next slide, please. Next slide, please. See, thank you. So it is customary to use n for the divisor. So a equal to nq plus r. So when you divide by n, the remainder can be 0, 1, 2, 3, 4, 5, 6, dot, 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 n minus 2, n minus 1. That is, if you divide by 12, 37, I divided by 12, the remainder is 1. 36, I divided by 12, the remainder is 0. 47, I divided by 12, the remainder is 11. So the remainders are between 0 to 11. Next slide, please. Now you see, I take any number and fix it. I will take a non-zero positive number and fix it. Now every integer we'll have one of these remainders 0, 1, 2 up to n minus 1. Say, suppose I fix 7. I have fixed 7. I will divide every integer by 7. Next slide, please. Every integer by 7. What will be the remainders? Either 0 or 1 or 2 or 3 or 4 or 5 or 6. Previous. Okay. Now just check. 63 is 7 into 9. So the remainder is 0. 45 is 7 into 6 plus 3. So the remainder is 3. Now consider the remainder of 63 plus 45, that is 108. 108 is 7 into 15 plus 3. So instead of adding, we could have adding to get 108 and then divide by 7. I could have directly added the remainders. But let me check one more times. So instead of 63, we will take 51, which is 7 into 7 plus 2. So the remainder is 2. The remainder is 2. For 45, the remainder is 3.
So 3.
51 plus 45 equal to 96. I can say for 96 when divided by 7, the remainder will be 5, and it is. Well, this can be proved. But I have given this, that remainder of L plus M when divided by 7 is the sum of the remainders obtained by dividing L and M by 7 separately. That means you want to find the remainder of L plus M when divided by 7. You divide L by 7, there is a remainder. You divide M by 7, there is another remainder. Add the remainders. You will get the remainder of L plus M when divided by 7. I have put one star there. Who can tell me the star, meaning of star? Can you tell me?
So multiplication.
No, multiplication also has this, but what happens if I take simple numbers? 13. When 13 when divided by 7, what is the remainder?
Sir, 6.
Yes, sir.
6. And next I am going to take 5. Okay, the remainder is 5. Now 6 plus 5. Now I am trying to find 13 plus 5, the remainder divided by 7. But here I am getting 6 plus 5 equal to 11. And 11 is greater than 7.
7.
Then what to do? Divide it by 7. Divide that addition by 7. You get the proper remainder. Therefore, that star is there. See, there is a clock mathematics. You have studied that clock mathematics, haven't you?
No, sir.
It's clock mathematics. Next slide. You have not studied clock mathematics? See, it's. Have you seen clock with 0, 1, 2, 3 up to 12? Then do you get 13?
No, sir.
In the clock, no. So what you are getting is 0 to 11 and then 0. Right? So when you divide by 12, what are the remainders possible? 0, 1, 2, 3, 4 up to 11. Next again 0, because if you to go round and round, when you complete the round, you will get the 24 hour, then 36 hour, 48 hours, all divisible by 12. Okay, I today woke up at 7. Okay. And I studied for 3 hours. It's 10. And then I slept for 12, whatever hours. You have this clock mathematics addition. You will get, say, suppose 7 p.m. I am there and I slept for 9 hours. So I got up at 16 hours. No,
No, sir.
I got up at 4 a.m. in the morning. Therefore, I have shown this circular thing. Yes. Now you see,
Sir, was that L plus M thing only valid for 7 when we divided by 7?
now any n. But now here it will be difficult to prove it. So can you show the slideshow, Aaron?
So he left the
Can
meeting.
you give me some 10 more minutes? Yeah, students, do you have notebooks with you?
Yes, sir.
You write down. Okay, those who have write down 1989 into 1990 into 1991. Now I am going to tell her
Sir,
1989
can you?
into 1990 into 1991. The same result applies to multiplication, that the remainder after dividing by 7 of the product of numbers is the product of the remainders. So can you tell me quickly what is the remainder when 1989 into 1990 into 1991? Yeah, I am repeating, Vedanti. The remainder of the product is product of the remainders. Remainder of the products is product of the remainders. So now consider 1989 into 1990 into 1991 and divided by 7. Oh, and I want to find the remainder. So first thing what I will do, I will divide 1989 by 7. So 7 2s are 14. Yeah. Yeah. Alicia, I will repeat. Remainder of the product when divided by 7 is product of the remainders when divided by the. So I divide one number by 7, take the remainder. Next number by 7, take the remainder. Instead of multiplying those numbers and dividing by 7 and getting the remainder, I will make division small. No need of multiplying big numbers. So I will get the remainder as product of the remainders. See, I have given a next slide, Aaron. So the rule is the sum or product of any two natural numbers has the same remainder when divided by any general as the sum of their remainders or product when divided by n. If sum or the product of the remainders exceeds n, then divide that sum or product by n, consider the remainder. Now, next, instead of doing much thinking on this, now this is my just one, yes. This was the example, find the remainder, which the number 1989 into 1990 into 1991 plus 1992 cube gives after the division by 7. Vedanti, will you multiply 1989 by 1990 by 1991? You will multiply. Should not. Why? Because 1989 is 7 into 284 plus 1. So 1989 gives me remainder 1 after dividing by 7. So 1990 will give me remainder 2 when I divide by 7. Is it okay for you? If 1989 gives me remainder 1, 1990 will also give me remainder 2. Okay? And 1991 will be giving the remainder 3. So by our rule, 1989 into 1990 into 1991, the remainder is 1 into 2 into 3, that is 6. That is 6. And 1992 gives the remainder 4. And 4 cube is 64, so I get remainder 1 there when divided by 6. So 1 into 2 into 3 for 1989 into 1990 into 1991, I get 6. For 1992 cube when divided by 7, I get 1. Addition of the remainders is 7. Oh boy, 7 divides this product. And without doing any calculations, I have shown this. Without doing any multiplication or cubing, I showed, and you showed those Goan students, excellent students, that 7 divides 1989 into 1990 into 1991 plus 1992 cube. Arun, next. What one would think next to impossible, we did quite easily. Because multiplying these 4-digit numbers 3 times and then calculating a cube and adding, we didn't do that. The next to impossible we did quite easily because we are now more powerful in mathematics. Next slide, please. Now I will go to application. Next slide, please. Because I will skip this example. If time permits, I am come. Okay, Vedanti. So next slide, Arun. Okay, next slide. I will come back to this example if you allow me the time, but let me first tell you the, yes. Have you seen the transactions in ATM? Have you seen somebody making payment by card?
Yes, sir.
Yes.
ATM
Yes,
and
sir.
card.
Yes, sir.
Yes, sir.
See, the thing is that, do you feel that whether it is secured, my transaction is secured? Because suppose I am sending Nikon, that is Samartha, 1000 rupees. Arshit should not know that I have sent him 1000 rupees. Because higher transactions for individuals, it may not harm that much. But for higher transactions between companies, confidentiality of financial transactions is very important. You go to ATM now, how they cheat is different, but most of the transactions do get through and very securely. So I will tell you very introductory part of this. See what is happening. I will tell you, when you insert an ATM card, there is a chip and some information is retrieved. It is sent to the bank. So my card is for Canara Bank. It goes to the Canara Bank head office, whatever their server. It is verified. How is it verified? This is so and so. Then I give my PIN. Then it is verified. Yes. The person who knows this PIN is this guy who holds this card, so it is correct. Then I type the number, again it is decoded. So there is a communication. So there is a communication of data. Now, when I am sending data, that data may get changed. I think in your early ages, you have done this. Say 4 or 5 persons are sitting in a circle. One tells the message very, very in the ear of the next person, very, very in small sound, very softly. Then he tells next, next, next. And again, the first person who originated the message hears the message what has been transferred and come to him or her. And it is different. Have you played this?
Yes, sir. It's Chinese whisper.
Yeah, so it it changes. And if my message changes, yeah, if my message changes for this transaction, at least I should know that the message that has been sent originally and that I have received is different. Yeah, broken telephone. But I should know that the message I have received is not correct. Right? Yeah. The message that has been sent and received by me, I should know whether it is correct or wrong. So the thing is, what we do is we can add a digit. So 8-digit bytes are there. You might have known that 8 bits form a byte. So bit is a 0101. So there is a, we add a ninth bit. We add a ninth bit so that there will be even ones in the message. So that there will be even ones. Just see odd even ones. Next slide. Next slide, please. You see the one back. Sorry, I said twice. Next slide, next slide. One. So 010100011. There are even one number of ones, and I go by even parity. So in the end, the bit I will attach is 0, so that the number of ones have remained the same, remained even. Now, while transmitting the message, there was a change. The second one was changed to 0. The second one was changed to 0. Now see what happens. The received message now is 000100110. The received message with the, see, originally it was even, so I had added the ninth bit at 0. Now the second one has changed to 0. I will not change the bit because I have done it already. Now the receiver sees that there are odd number of ones. There are odd number of ones. So he understands that there is some mistake in the message. He tells, send the message again. Send the same message again. Send the same message again. So next slide. So it is only good for 1 bit errors. So if one changes 0 to 1, then it can be done. However, there are methods based on this n boxes of 0, 1, 2, n minus 1. You can understand. I will definitely decide that the remainder of this should, after divided by 4, should be this. Either 0 or 1 or 2 or 3. I can adjust it. Right? I can adjust it by writing the last bit as 0, 1, 2, 3. That is done. Or I can break into pieces my message and do it. Yeah, Aaron, I can take how many more minutes? Aaron ji, can I take 5 minutes more?
Yes, sir. Yes, sir. You can take 5 minutes more.
So you go back. I skipped some nice examples, so let us go back. Go back. Oh, okay. Stay here. Let prove that n cube plus 2n is divisible by 3 for any natural number. Oh, is it a typing mistake, Ankit? Must be. Should be checked, but actually, let n be 2 because it's very, very generalized statement. It claims something beyond it. Any natural number, take its cube and make double of it and add. See, n cube plus 2 times n, always divisible by 3. That means you are telling me infinitely many statements. So 1 cube plus 2 is divisible by 1001 cube. 3 plus 2 into 1001 is divisible by 3. Have you
Sir,
understood?
I checked with 2 and 3, it is divisible by 3.
Yeah, but may not be for 4. May not be for 4. You are checking for 4. Then I will say may not be for 31. Then suppose Ashwath tell me that I have checked for till 1000. Then I will say may not be for 10,007. Here the power is I am going to try and prove it. I cannot write on whiteboard, but so I will tell the statement slowly. See, yeah, I want to prove that it works for all natural numbers. When divided by 3, you see, when divided by 3, what are the remainders possible?
So 0, 1, 2.
Yes, 0, 1, 2. Okay. So the remainder is 0 means what? N is divisible by 3.
3.
Correct. If n is divisible by 3, there is no problem. N cube is divisible by 3 and 2n has to be divisible by 3. Isn't it?
Yes, sir.
Right. 3 cube is divisible by 3 and 2 into 3 is divisible by 3. No problem. And so all the integers are now in the boxes that remainder 0, remainder 1 or remainder 2. Okay? They are in remainder 0, remainder 1, remainder 2. Again, the infinitely many integers in the box of remainder 0 do satisfy this, that n cube plus 2n is divisible by 3. Now, what about those who have remainder 1 when divided by 3? That is like 4. So 4 cube is 64 into plus 8. 64 plus 8 is 72. It is divisible by 4. Now 7, but I don't know, 7 cube. Okay, means whatever. 383 plus 14 is divisible by 3. But how long I will check? But then see that Gaurav is saying that क्या sir आपको ये मैं बताता हूँ. You only have to check the remainders. And you are saying when divided by 3, the remainder is 1. So if the remainder is 1 of n when divided by 3, what will be the remainder of n cube? It will be 1. It will be 1
Yes,
by
sir.
our this thing. And again, what about 2n? n has remainder 1. So 2 into 1, the remainder is
1.
2. 2 into 1, 2.
Yes, sir.
So the
Okay.
remainder is C. The remainder is 1. Consider 4. The remainder divided by 3 is 1. So 2 into 4, 8. The remainder is 2. Because see, it's 3k plus 1. 3k plus 1 into 2 is 6k plus 2. But 6k is divisible by 3 and the remainder is 2. For n cube, remainder was 1. For 2n, remainder is 2. And 1 plus 2, 3 is remainder. 3 is remainder. How can that be? Because the remainder is between 0,
Sir, it
1,
should
2.
be 0.
It should be 0. Means what? N cube plus 2n is divisible by 3.
3.
When the remainder is 1. Now what about remainder 2?
Sir, if the remainder is 2, n cube will be 8. The remainder of n cube will be 8, and the remainder of 2n will be 4.
Okay, so 8 plus 4, 12, which is divisible by
3.
great. Oh. Have you understood
Yes.
what you have done?
Yes, sir. Yes, sir.
Yes, sir.
By 3 small calculations, you have proved infinitely many statements. How many integers are there? Infinite. Does this statement that n cube plus 2n is divisible by 3 pertain to any and every natural number? Yes. So in fact, these are infinitely many statements which you have proved in one stroke.
Yes, sir.
So now, are you more powerful in mathematics?
Yes, sir.
Yes, sir.
Do you realize what you have
Yes,
done?
sir.
So let us move ahead, Arunji, in the slides. Move ahead. So let us come back to the application. So there are better systems of encoding, decoding, and error detection, but they are all using and the techniques introduced in this lecture. A very interesting mathematics can be used in maintaining the state-of-art technologies like ATM, data handling, signature protection, GPay, and so on. Next slide. This lecture has introduced to you basics of some topics of number theory. We played with numbers, that to integers, and that too most of the time natural numbers. So it is called number theory. It is a rich subject. But then if you feel now this was an interesting lecture, or as Avita thought that I was better in this than the lecturer, or whatever reasons, if you want to study this subject further, these are the books. You can write down. And also my presentation is with Arun sir. Have you written down?
Yes, sir.
Yes, sir.
Yes,
Next
sir.
slide.
Yes, sir.
Yes, sir.
So this is something just to show nice thing, but here also the parity, if you rotate by 60 degree or some degrees, you will look this as same. Since this is pentagon, that degree is slightly
So
different.
72 degrees.
Next, not 72. Okay. Oh yeah. Okay. Yes, 72. So thank you. It was great to be with you. Initially, there were hiccups. I don't know. I have given lectures on Meet, but somehow I could not do that today. But it was great. You interacted well with me. You guessed the answers. Thanks. Thank you.
All right. Thank you, sir, for that wonderful session. I'm sure all the students enjoyed it.
Yeah.
Okay. Students,
Thank you,
did you
sir.
all enjoy the session?
So when are you sending the quiz link?
I will be sending the quiz link now. I was about to get to that. Okay. So before that, I would just like to thank Kiran sir as well as all the speakers who have dedicated their time to share their knowledge to all our students. I hope all the students enjoyed these sessions and all the sessions that we had this week. And I'm sure that whatever you children have learned in the past few days will help you in your life. On the behalf of the Infinite 3D team, I would like to thank each and every one of you who have attended this webinar. Thank you and have a good evening. I will be posting the link for the quiz right now. Students, please keep an email as well as a phone number ready. Okay.
So, Arun, can
Yes.
I leave? Because you may keep the session going on. Na?
Yes, I will keep. Okay.
So, I will leave and thank you, Arun.
Thank you, sir. Thank you so
I
much.
took a lot of help from you, and it was a very well arranged lecture. Students are beautiful. You are doing great work. Keep it up.
Thank you, sir. Okay, students, the quiz link is live in the chat box. You can go and answer the quiz. Thank you and have a good evening.
Thank you, sir.
So where we will get the results?
We are posting its results almost every day on our Facebook. So you can go to the Infinite 3D Facebook and check the results.
Okay, sir. Thank you, sir.